Hi Year 11, this is the first of 4 videos for the topic of probability. In this topic we're going to cover probability, then set theory, the laws of probability, and finish with conditional probability. So everything in this first video you should have covered in junior school, so starting in Year 7 or Year 8 and then repeating it in Years 9 or 10. The probability that a certain event happens is just a measure of its likelihood or chance. And numerically, probability is a number between 0 and 1, where 0 is impossible, 1 is certain, and 0.5 we say is 50-50 or equal chance. There are two types of probability. There's experimental probability and theoretical probability. Now, experimental probability, and we also call that relative frequency, it's based on the data that we get from repeated trials of an experiment. So for example, you might toss a coin 100 times. Here's the formula that we use. The probability of some event, say that we throw heads, is the number of successes, so how many heads we throw, divided by the total number of trials, so how many times we tossed the coin. Let's look at an example. I toss a die 150 times and record the results. So in my table I have the outcomes 1, 2, 3, 4, 5, 6. F stands for frequency, so how many 1s occurred, how many 2s, 3s, etc. And relative frequency is experimental probability. So to work this out we do 29 out of 150 and then times by 100 to make a percent. And all of these relative frequencies should add up to 100%. Now let's look at some questions. So based on our data, which number is most likely to occur? Well, this is the highest relative frequency, so it's a 4. What was the probability that we would get a 3? So find 3 and look across here, 15%. Is the die biased? So if it's a fair die, then all of these frequencies should be the same. But we've only tossed the die 150 times, and that's probably not enough. We're going to have a look later on what happens when we toss the die more and more times. The sample space of an experiment is the set of all possible outcomes. So here's our previous example. A 6-sided die is tossed. Write the sample space. And this is how we write it. So we've got 1, 2, 3, 4, 5, 6 in curly brackets separated by commas. The number of elements in the sample space can be written as n and then in brackets s. So this means the number of elements in the set S. We're going to look more closely at set theory in our next lesson. And now we'll move on to theoretical probability. It's almost the same formula as experimental probability. We have the probability that E occurs. It's going to be equal to the number of ways that E can occur divided by the total number of possible outcomes, or the sample space. This means the number of elements in the set E divided by the number of elements in the set S. So what is the difference between experimental probability and theoretical probability? Well, as the number of trials increases, the experimental probability approaches the theoretical probability. Let's return to our die tossing. Now, if we only have 10 trials, the probabilities are all over the place. We didn't even get any 1s. But as the number of trials increases, these probabilities get closer and closer to one another, until we get to n is equal to 5,000, so 5,000 trials, where they're almost the same. Now remember that the theoretical probability for all of these numbers is 1 out of 6, or 16.7%. And you can see that that's what these numbers are approaching. Now, compound events occur at the same time. For example, if we tossed a 6-sided die and a coin together, that would be an example of a compound event. Now, compound events can get quite complicated when we're trying to list all of the elements in a sample space, and there are various methods that we use to help us with this. We're going to have a look in the next example at how we use a list, but a grid can be helpful, particularly if we're talking about rolling 2 dice. We also use tree diagrams and Venn diagrams and two-way tables. Here's our example. A coin and a die are tossed together. List the sample space for this experiment. So we need to consider both events. The coin can land heads or tails. The die can land 1, 2, 3, 4, 5, or 6. So here's the sample space. Heads 1 up to heads 6 and tails 1 up to tails 6. There are 12 possible outcomes altogether. It's important to be systematic when you're listing the sample space. Now let's find the probability that we toss heads and a 1. So how many ways can that happen? Only one out of a total of 12. So the probability is 1/12. Find the probability that we get an even number or a tail. So we could have this one, this one, this one, or any of those. Count them all up, we have 9 out of 12. Now you can reduce that down to 3/4 if you want to, but you don't have to. And then finally find the probability that we get heads and a number greater than 4. So we want heads and a number greater than, not equal to, 4. So it's only this one, heads and 5, and heads and 6. So 2 out of 12. And then finally for this lesson, we're going to talk about the complementary event. The complementary event of E, we can either write as E with an apostrophe next to it, we actually call this a grave, or E with a line over the top. And you're going to see both notations depending on the textbook. The complementary event contains all the elements that don't exist in E. And here's the thing, the probabilities of E and its complement must add to 1. And we quite often use this formula. The probability of the complementary event must be equal to 1, take away the probability of the event itself. Let's finish with an example. John writes the letters of the alphabet on cards, so one letter on each card, shuffles them and draws one. Let A be the event that he draws an A. Show that the probability of A plus the probability of the complement of A is equal to 1. So what's the probability that he's going to draw an A? It's 1 on 26, isn't it? How about the probability that he doesn't draw an A? Well, that's all the other letters, 25 on 26. And if we add those up, we do indeed get 1. Okay, that's it for this lesson, short and sweet. In our next lesson, we're going to look at set theory.